quickly review some of the types of catalysis that is, or the mechanisms of catalysis that are utilized by enzymes, and also remind you what this energy diagram looks like. So we have energy increasing. The x-axis is the reaction coordinate, so the progress of that reaction. And we're just going to talk about this in terms of more activation energy and catalysis and delta G. So let's say this is the graph of an uncatalyzed reaction. So this one is uncatalyzed. And at this point we have E plus S. Here's our transition state, which is an ES complex. And down here we have E plus P. And in this reaction, our enzyme and substrate has more energy than our enzyme and product. And I just want to point out, in chemistry, this would be labeled E sub A, energy of activation. Biochemists label it differently. It's the delta G symbol, and then this line with two strikes through it. But that means the same thing as energy of activation. So that's the hurdle that has to be overcome for substrate to be converted to product and the enzyme released. And remember, the definition of a catalyst is what? What, GT? It lowers the activation energy. It doesn't get consumed. It's released at the end, or regenerated in some equations or reactions. So, catalyzed reaction. And again, I'm not a very good artiste. We still start with E plus S. Here is our activation energy, so it's much lower than that of the uncatalyzed. And here's our, this is catalyzed. And we have ES and EP, so this has been converted when we went up this hill, but it hasn't been released till we get down here. Okay. But basically the point of this graph is to show you the differences in the activation energy. Now one thing that doesn't change is Gibbs free energy, or delta G. And this is the delta G for this reaction. And it doesn't matter which path we take, the free energy is not changed. It's the same. So all we're doing is lowering the activation energy, which allows the reaction to occur at a increased rate, or reach equilibrium at an increased rate. Okay. So there were, I think, mentioned 3 types of catalysis, or 3 mechanisms. So what are enzymes, number one? Should ask. Yeah, they're proteins. So what are they composed of? Amino acids. Yeah. And Chris, I saw that email. I just didn't get a chance to look at that you sent right before class. Or sometime I was in the help room. It was about one of our amino acids, but we can maybe talk about that later. First is acid-base catalysis. And let's see. I'll post this. I'm not going to redraw it, but I'll post this in D12, maybe in that. Well, actually, it'll be in this video. Never mind. Forget what I'm doing here. So here's a look or a figure that shows you some of actually amino acids that can act, and depending upon their charge state, can act as either proton donors or proton acceptors, and that, of course, affects whether they're acting like an acid or acting like a base. Okay. So, in general, acids are proton donors, bases are proton acceptors, and so we would expect to see glutamate and aspartic acid or aspartate acting as proton donors. They're acids. Their base form is the deprotonated, which can accept a proton. Lysine and arginine, they're basic. In the protonated state, though, the side chain's protonated state, it can act also as a proton donor. So at physiological pH, it would be a proton donor. When it's in its unprotonated state, it could act as an acceptor, but also consider what pH that would be. Cysteine has that thiol group, which behaves like a hydroxyl group, so it can donate a proton or accept a proton. Histidine can act as a proton donor as long as it's in its charged state, the side chain, base and other. So depending upon the local environment in an active site of an enzyme, some can be slightly more acidic or basic, so histidine may or not be protonated. So it just depends. Serine, also threonine would fall into this group. I don't know why it's not listed, but with that hydroxyl group, it can donate a proton, and so could tyrosine. So essentially, this is going to be some type of proton transfer that's occurring in that active site that helps stabilize the interaction and allows the catalysis to proceed. So that was acid-base. 2, the second mechanism is covalent catalysis. And this is actually going to be a result of an actual covalent interaction between that enzyme and substrate that stabilizes it. And I had here are some enzymes that utilize this mechanism, and actually we will see all of these enzymes when we start looking at our metabolic pathways. Well, trypsin and chymotrypsin we've seen in our protein problems, but glyceraldehyde 3-phosphate dehydrogenase, phosphoglucomutase. We're going to see all of these in one of our metabolic pathways or another. And this just indicates what the reacting group is. So this is the amino acid that is interacting with the substrate, and this is what the covalent intermediate is. Okay. We'll specifically look at these when we look at the pentose phosphate pathway. So we'll see that again. And then finally there's metal ion catalysis. And as this suggests, a metal has to be present for this reaction to occur. And at least 1/3 of all known enzymes require metal ions to work. And when we look at those metabolic pathways, we will see those metal ions associated with the enzymes that are catalyzing the reactions that we look at. So there are two, we can classify these enzymes in two ways. There's a group called the metallo enzymes, and these contain a tightly bound metal ion. So they're kind of always present and part of that enzyme. And some of the ions that we'll see in these metallo enzymes, Fe2+, Fe3+, zinc 2+, we'll see manganese 2+, and cobalt. And the other group are metal activated. So in order to actually catalyze the reaction, they have to be activated by a metal ion. And these just loosely bind ions like sodium, potassium, magnesium, or calcium. So these are the ions that we're going to see in those metabolic pathways. So they have to be present for that enzyme to function, but they're not if there's no sodium or calcium there, whatever it requires, it's not going to be activated. Okay? So it's kind of regulatory. So those are the three primary or most common catalytic reaction mechanisms. So let's look at enzyme kinetics, because I want to go through at least two problems with you before we part today that hopefully will help you with your case study. So I will probably still do a smaller video that kind of refreshes your 1062 memory, and you've got a couple or a page or so in your packet that you'll be able to take notes from that. I'll try to get that up on Friday. But with respect to enzyme kinetics, I'll go back to inorganic chemistry. when you studied rates of reactions then, you said the rate was equal to K, and I'm going to just say a first order reaction, and these only include reactants. So this would be an example of A going to product. And that's what that looked like in 1062 or Gen Chem 2. We also in enzyme kinetics can write a similar reaction, S going to P, substrate going to product. These are both first order reactions. So same as A to P. However, when we write the rate of this conversion, we use velocity. So V equals K times the concentration of S. And K is a rate constant that is specific to that reaction. And for first order reactions, the units of K are 1 over S, or you could write it as S to the minus 1. And K basically tells us how quickly S is going to be converted to P for product. So Michaelis-Menten they came up with a mathematical relationship between velocity, velocity maximum, substrate concentration, and something else we're going to call Km, and we'll talk about those. So initial velocity is just V naught. And if we plot data that results from the Michaelis-Menten equation for an enzyme catalyzed reaction, the y-axis is the initial velocity, and this is concentration of substrate. Sorry, didn't need to do that. And it will look like this. So it's hyperbolic. And where we reach this equilibrium, substrate binding essentially equals substrate releasing. So we can't get any more substrate bound. Okay. And this is the Vmax. So that's the maximum velocity that can occur with that concentration of substrate. Other points on this, something known as the Km, and this is the Michaelis constant, which is also it is found at 1/2 Vmax. Let's put that on there. The equation itself is initial velocity equals Vmax. So Vmax is on top. It's on top here, and we're going to multiply Vmax by the concentration of substrate. And then we have Km, plus the substrate concentration on the bottom. And you need to be able to use this equation and manipulate it. Okay. And we'll do some examples of that. Now, we can actually get a view what's going on a little better with a Lineweaver-Burke plot. So basically, this is just a double reciprocal plot. We aren't going to work with that that equation. It's not fun. But I want to draw two lines here for you. This one. This one. Okay. So these two lines are very, well, I'm sorry. It shows the change when we have a high enzyme concentration versus a low enzyme concentration. So, obviously we have a slope, and the slope is equal to the Km divided by Vmax. And that applies to both of these, of course. The y-intercept is 1 over Vmax. And so that's for both of those. And, oh, I'm sorry, this is 1 over initial velocity versus 1 over substrate concentration. I'll label those for you. And this is negative 1 over the Km. So you'll see that Vmax is affected by enzyme concentration. Obviously the slope is influenced by enzyme concentration, but not the Km. The Km is constant, always constant, because it's specific to that enzyme. And I know I mentioned these briefly in one of those videos, but we're going to be working some problems now that use these, and we're going to, I just want to remind you what catalytic efficiency is. And it's basically a specificity constant. So how specific is that enzyme to its substrate? You know, usually enzymes are pretty specific, but there's some that get a little loose. And so the looser they are, the less efficient they are. But this is calculated by kcat, which is the turnover number, divided by the Km. And we'll talk about kcat in a minute. So this is a second order process. And so it has units of 1 over m times s, or again, we could write that 1 to the m minus 1, s to the minus 1. The maybe I should have done kcat first. Kcat is basically the turnover number. So how many substrates are converted to product in a certain amount of time. And this is two things, actually. We can calculate it using Bmax over the total amount of enzyme, if we have that. Otherwise, it's simply equal to K2. So what does that mean? So when we write or represent the reaction that is occurring between enzyme and substrate, the first step is reversible. Okay. So there's a K1 going, and that is for the forward reaction, and for the reverse, we've got a K subscript -1. So that enzyme is, or that substrate is off and on that enzyme. The K2 applies to when that enzyme actually converts substrate to product. So turnover number is also equal, or the kcat is also equal to K2. Okay. And so let's get a problem, because I want to at least get through one. Actually, I want to do both of them, because they're a little different. So I just picked two from the end of your chapter, and I'm pretty sure I've suggested practice problems. So there are others like these, and I recommend that you try them. But so I picked 9 and 10. Number 9, we're given a K1 equals 2 times 10 to the 8th. And this is m-1 seconds minus 1. We're given a K2, 5 times 10 to the 3rd, s to the -1, and the K reverse. And sometimes you might see those as K subscript F for forward, K subscript R for reverse. Your text uses the 1 and -1. And that's 1 times 10 to the 3rd. They don't use very good sig figs. 1 is awful. But anyway, that's me. So our first question is, what is KS? You might also see this as KD. And basically, this is the dissociation constant. Lots of constants. For ES. And so KS is simply K subscript -1 divided by K subscript 1. So you're just plugging in those numbers, and what we had 1 times 10 to the 3rd, s to the -1 over, did I miss something? You know what, this was, I got a molarity in here somewhere that I don't think I should have there. No. Where did I put that? Here. Sorry. No, that was supposed to be there. That was second order. Okay, never mind. Then we have 2 times 10 to the 8th, m-1, s-1, yeah, because we want this in a concentration. These are going to cancel, and we have 5 times 10 to the -4 molar, or 5 micromolar. And we're going to talk about how do we get that to micromolar? So one thing you're going to have to be careful with these problems, and I'm going to have to start rushing, I think, is watching the concentration units. So you may have to be doing some conversions. And I think in the next one, show that to you. So in B, we're asked, what is the Km? And so this is the Michaelis constant for the enzyme. And the Km is equal to K1 plus K2 divided by K1. So we were given all of these numbers. We have 1 times 10 to the negative third, 10 to the third, s to the minus 1, plus 5 times 10 to the third, s to the minus 1, and that will all be divided by yeah, it's the 2 times, I have the wrong number in there, sorry. So will someone, because I didn't use K1. I did down here, for some reason I didn't in the top. Can someone calculate that for me? Oh, so this would be 2.8 times 10 to the 8th s to the minus 1. I don't know. Screwed that up. Sorry. You got 1?
Yeah.
You know what? I think this is supposed to be -1. I'll double check that and correct this. I think I wrote the right thing, I just didn't write the right thing here. I'm pretty sure that's -1. So we'll come back to that, or I'll send you a note about that. One thing that I had to do well, I didn't have to do it, but let's just do it. Let's say we have 3 times 10 to the negative 5th molar, and we want to convert that to micromolar. So this just means that I've got 3 times 10 to the negative 5th moles in 1 liter. And if I want to convert to micromolar, I just need to convert those moles to micromoles. How many micromoles, well, I'm not doing anything with the liters, but how many micromoles in a mole? 1 mole is equivalent to how many micromoles? Micro?
10 to the 6th.
Yeah. 10 to the 6th micromoles. So this becomes 30 micromolar. Yes, this will be micromolar. This was M minus 1, S minus 1. It will have units of molarity, yeah. And let's see. C, in this problem, we were asked, what is K-cat? So again, this is the turnover number, and we can either calculate it we can calculate it if we have V max and the enzyme total. We don't have that. What else do we know? that K-cat also equals what? Yeah, and we have K2, so K-cat is 5 times 10 to the third s to the minus 1. D, in this problem, what is the catalytic efficiency? And that is K-cat divided by Km. And so we know our K-cat is 5 times 10 to the third s to the minus 1. And that's divided by 3 times 10 to the fifth molar. So our catalytic efficiency is it negative? Where is it? Yep, sorry. I lost track of myself. (1.67) times 10 to the 8th m to the minus 1 s to the minus 1. Yeah, sorry about that negative. Oh, yep, so that's it. And then 10, this is one I really wanted to make sure we got through. This is one of the glycolytic pathway enzymes, triose phosphate isomerase, and this catalyzes the conversion of glyceraldehyde 3-phosphate and I'm just going to shorten that to a P. We'll use some notation when we go through that pathway. To dihydroxy acetone. I've got to split that up too. Phosphate. Okay. And this is a reversible reaction. Okay. And let's see, we are told that the Km for this enzyme is 1.8 times 10 to the negative 5th molar. And then we're told when GAP3, which is glyceraldehyde 3-phosphate in notation, is 30 micromolar, the rate of the reaction, which RxN is my abbreviation for reaction, is 82.5 micromole mil to the minus 1 s to the minus 1. And rate of the reaction is velocity. And we need, we're asked to find Vmax. So what is Vmax? So that means we need to use that Michaelis-Menten equation, where velocity equals Vmax times substrate concentration divided by Km plus substrate concentration. And so we've got velocity. We have our substrate concentration because our substrate is glyceraldehyde 3-phosphate. And let's see. Oh, we're finding Vmax. So we need to rearrange this to solve for Vmax. So say Vmax, times substrate concentration, equals velocity times Km plus substrate concentration. And then further rearranging that, Vmax then will equal velocity times Km plus substrate concentration over substrate concentration. So now all we have to do is plug those values in. Our velocity is 82.5 micromole per mil minus 1 s minus 1. And that's going to be times the sum of the Km and the substrate concentration, which is 18 plus 30, and that's micromoles. Substrate concentration is 30 micromoles. So micromoles are going to cancel here. And our Vmax equals 132 micromoles mil to the minus 1 s to the minus 1. B, we are told that, I'm just going to write it succinctly here, E total equals 3 nanomoles of enzyme per mil. And so that is our E total. What is the Kcat? Now, we've already calculated Vmax. Here we don't have a K2, right? So we actually have to use this equation, Vmax divided by enzyme total. And we calculated Vmax to be 132 micromoles mil to the minus 1 s to the minus 1, and our E total, oh wait, I have to, problem here, what's the problem? Units. Yes. So we have nanomoles and our Vmax is in micromoles, so we have to get those to the same unit. And I actually used moles. So micromoles, so what do we get? Micromole. How am I going to convert that to regular old moles? We have 10 to the 6 micromoles in 1 mole, right? So that means I have 132 times 10 to the negative 6 micromole, or moles, sorry. Okay. Do the same thing for nanomoles. Nanomoles, nano is negative 9. So when I rewrite this again, Vmax over divided by enzyme total, my Vmax is going to be 132 times 10 to the negative 6 mole per millisecond divided by 3 times 10 to the negative 9 mole per millisecond. So my Kcat, mole per mil, I'm sorry, that shouldn't be there. my kcat is 44,000 s to the minus 1. $44,000 per second. That is great turnover. And one more, catalytic efficiency. Catalytic efficiency. What was I just saying here? Specificity. So catalytic efficiency is that kcat divided by the km. And we just calculated kcat to be 44,000 s to the minus 1. Our km was 1.8 times 10 to the negative 5 molar. So this gives us 2.44 times 10 to the 9th m minus 1 s minus 1. Any questions?
Where exactly are you getting your problem for?
Your book? Yeah, they're at the end of each chapter. And I suggested practice problems in your weekly readings. Yeah, so that's all I have.